Oh, okay.
Thank you.
Yeah. Yeah. So let me just go back a bit. So like we are saying, this process per the attribute given, okay, which is a fixed probability of success, and then independence events, okay, and then we're also looking at the probability of the first occurrence after a number of what events, okay, makes the process what a geometric process. And to find the probability of a geometric process, we saw the formulas earlier, okay, which is Q, okay, raised to the power what, K minus 1, okay, and then times what, times P. Here we've been given the probability of success at 0.25, and then the probability of failure will be what, 0.75. Okay, good. So you just fix it in the formula and then do the calculation. I'm sure you are doing it by now. So 75 raised to the power 3 minus 1, which will be 2, times the probability of success, which is 0.25. So by now you should get the answer for me if you're working. So what are we getting? What do we have?
So 0.141.
So 0.141. Okay, thank you. So that is the probability of observing a child with blood type O after 3 events or after the first 2 events. Okay. Then if you want the expectation, like we know expectation is just what? But the formula is 1 minus what? 1 over what? P. Okay. So you just make use of that. That will be 1 over P. Okay. And your variance will be what? Your variance of the process, okay, is what? Q is going to be Q, which is 1 minus P, okay? So 1 minus P over what? P squared, okay? So once you calculate it, you get the variance of this process. Okay, so moving on. Yeah, the next distribution statistical model we are looking at is the Poisson process. Okay, now what do we mean by the Poisson process? Poisson process is used to model arrival rates within fixed time intervals or within fixed intervals. Okay, good. So let's say you've defined time intervals of 24 hours and you want to see the number of planes that will land at an airport, okay, within the 24 hours. Then we are looking at a Poisson distribution. Or you define your time interval as maybe 1 hour and you want to see the number of people who are entering the bank, okay, within the one hour period. That is also a Poisson process. Okay, so the context is the number of events occurring in a fixed period of time. Okay, and it says events occur with a known average rate and are independent. So there should be given, you should be given a rate of occurrence or a rate of arrival. Okay, and then you should also be told that the events are occurring independent of each other. Okay, so once we are given a Poisson process which is characterized by the average rates which is lambda, okay, given a fixed time, right? Then we can model such processes like the number of cars passing a fixed point in 5 minutes. So that's traffic lights modeling and simulation. Okay, the number of calls received by a switchboard during a given what period of time. That goes into various fields of study, telecommunications, okay, into security and all that. The number of messages coming to a router per second. I think we all understand that. Number of travelers arriving to the airport for flight registration given a time. Okay. So usually your average rate will be a number of cars or number of people per some time. Okay, like you have 3 cars per 5 minutes. Okay. Then again, the probability distribution of the process, the PMF, is what you have here. Okay. So it's just giving us lambda raised to the power k times e raised to the power negative lambda over k factorial. Okay. Some books will write k in terms of x. So you see lambda raised to the power x, e raised to the power what? Negative lambda, okay, over x factorial is the same thing, okay, where n is the number of what? Arrivals, okay, very good. Now the CDF of the process is also given by this. The CDF is the cumulative density what? Function. Okay, so if I ask you, if you identify the process to be a Poisson process and you are supposed to plot the probability mass function of the process, then this is the function you use, okay, your program. If you are plotting the CDF, this is the function you are going to make use of. Okay, very good. So you take note of that. And there is a plot for the CDF here, okay, which we can investigate, okay, at home with our MATLAB. Okay, so you just try that at home with your MATLAB program. Okay, moving on. Yeah, so further properties have also been provided. The expected value is lambda, the variance is lambda, okay? So expectation of the process is lambda, variance is also what? It's also lambda. And then the PDF of the distribution tool has been provided. Okay, the mass function of the distribution has been provided. So we can see the nature of the Poisson process. Okay, later on in validation process, we will come to a data set which we'll be using, which looks like a Poisson process, and we'll have to identify whether indeed the process is a Poisson distribution. Okay, to do that, you first have to know the nature of the graph, the probability distribution for the Poisson. Okay, how we can see it's looking somehow like the chi-square is skewed to the right, okay, giving a certain fixed probability. But whilst the probability also moves to giving a certain probability and a certain number of occurrences, we can see that the process then starts looking like it is a normal process. Okay, let's move on. Yeah, so there is an example here. He says that the number of cars entering, he says the number of cars that enter a park. A parking follows a Poisson distribution with a mean rate of lambda, which is equals to what? Which is equals to 20 cars per hour. The probability distribution of having exactly 15 cars entering the car park is provided in the solution below. So just examine the solution carefully. Okay, so that is also estimated, like we know, with the density function. Okay, so it's just a matter of us using your lambda raised to the power x. Then we have e raised to the power negative lambda, okay, over what? X factorial. Okay, so you can do the calculation and then cross check to see if you're also getting the answer. Just confirm if you are getting the answer. E is the exponential value, okay? E is the exponential value, not raised to the power, okay? So we are having the exponential value. Here, lambda has been provided as 20 cars, okay, per hour, okay? 20 cars per hour. Okay. I'm sure you would have verified that solution by now. Now, another way of getting these two is because we are dealing with a density function, you can also find the CDF because we are acting for the probability that exactly 15 cars arrive within the parking in 1 hour. So you can find a CDF in 15 for 15 cars and then find a CDF for 14 cars. CDF means you would have sum all the probability till you get to 15 and then sum all the probability till you get to 14, right? And then once you subtract, you come to the same conclusion. As we saw earlier, the CDF function, okay, we saw that earlier here. So if you want to find the CDF, you are going to make use of this function here, okay, to find the CDF, where your I this time is equal to what? 15. So if you want a CDF at 15, okay, and given your arrival rate, okay, you are going to get 15 factorial lambda, which is I think 25 raised to the power 15 e raised to the power negative lambda. That will give you the CDF, okay, for that value. Then you find for 14 as well, where k is equal to 14. When you subtract, you get the probability of 15 cars arriving at the park. Okay, the same way this is also CDF. It says find the probabilities of having more than 3 cars. More than 3 cars is indirectly 1 minus the probability of having less than 3 cars, okay, less than and equal to 3 cars. So you can also less than or equal to 3 cars simply means you are going to find the probability of the cumulative distribution, okay, till you get to 3 cars, till you get to 3 cars, okay. So either you use the CDF to find the cumulative distribution till you get to 3 cars, or you can find the probability at x equals to 0 using this function. So you make this 0, okay. Then you find the probability at 1, the probability at 2, the probability at 3, and combine them, okay. That will also give you the CDF. It's going to be the same thing, okay. Then once you combine, you subtract 1 from 1 to give you the probability of what? Of observing more than 3 cars entering the parking area in 1 hour. Okay, so moving on, are there any questions so far? Any questions, class? Any questions? Okay. If there are no questions, let me move on. So the next thing we have to take note of is in the case where your Poisson process is defined. For example, you were given the rate as, let me clear this first. So we're giving the rate for an hour, okay? But you are told to find the probability of having exactly 15 cars entering the park in 2 hours, okay? In 2 hours. In 2 hours means that your interval has multiplied by 2, okay? Your initial defined interval is 1 hour, okay? So you've increased it, okay, 2 times, okay? Which means that your distribution function will be modified a little bit. Okay, now it's going to be not just lambda, okay, we are going to have lambda, okay, t raised to the power x, okay, yeah, I think we are using k, so I'll keep k here, okay. Then we have e raised to the power negative what? Lambda t, okay, over your k factorial, okay. That is how it's going to look like. So anytime your interval is increased, then you also have to increase. So in this case, your t is the 2 times step, so it becomes lambda times what? Times 2, okay. So you take note of this one. Let me see if there is an example there for us to solve. Okay. So an example, let me see if we have an example there. Okay. Yeah, okay. So we have some more notes. It says for the Poisson process, NT, no, let me reduce the volume. So it says for a Poisson process,